Good afternoon. Here we are again for another lovely session of ENGR 2302 Engineering Dynamics. All right, so today we're going to continue on. This is going to be the 18th lecture in this series. Where has the semester gone? It's amazing how quickly it has passed. And we are going to work today with an introduction to three-dimensional motion. An introduction to three-dimensional motion. Now, we're not going to cover this in incredible depth. It can obviously be a very involved topic, but I just want to introduce a few basic ideas, a few basic topics to make sure you get some exposure to this material. So there are some cases where, now most of the problems we work with, we've been working with plane motion, but there are some problems where three-dimensional motion or three-dimensional consideration is necessary, especially things like gyroscopes. If you're doing any kind, a very common example or modern example would be something like robotics, where you have if you think of, say, an assembly robot where you have the, think of a video or a picture, or I'm sure you've all seen of, say, an assembly line where you have a robot arm or something moving around, making welds, making connections, bolting things in place, stamping pieces, all of this kind of thing. And think of how, if I have a robot arm, imagine this. Imagine if I want to move a robot arm. Well, that's not a two-dimensional problem. I need to do that in 3 dimensions. And it's not simply a matter of, tell it to go to this position. When you think about it, if you're going to tell a robot arm to move and to twist and to rotate and things like that, you need to make it so that that arm is not only at an appropriate position, but it's at an appropriate position when you want it to be at that location. And so you need to start considering things, not only do I want the tool at the end of the robot arm to be in the right location, but I want to make sure that it has a certain speed or has 0 speed when it stops its movement. So it's not just that I accelerate it, and it's not that I cannot just instantly accelerate it, move it over here, and then instantly stop it. I have to take into account that it's going to take some non-zero time to both accelerate that arm and decelerate that arm. In other words, I had to start thinking about the actual momentum of the robot arm and the part that it's holding, rather than just say, rather than just telling it, move this part to this location here. Things are much more complicated than that when you start dealing with actual heavy 3-dimensional objects like you would in, say, a factory. So let's begin then. Okay, so let's consider this here. Okay, so motion in 3 dimensions, or kinematics in 3 dimensions. Kinematics in 3 dimensions. Actually, I shouldn't say kinematics. I should just say dynamics. In 3 dimensions, I want to be a bit more general than that. Dynamics in 3 dimensions. Okay. So we did develop some basic relationships in 2-dimensional systems, but these can be extrapolated into 3 dimensions. So the basic properties of a system in 2 dimensions can be extrapolated to 3. In other words, if I look at something in terms of, if I look at a plane system, consider my general plane system here. Well, if I had a plane system like this, well, actually, let me just draw my potato again, my famous purple potato. Or my general rigid body. And for our potato here, we have mass center here, etc. And if I applied a variety of forces to this, say just F1, F2, F3, etc., when applied to this rigid body, these would then be equivalent to two things. One, some change in the angular momentum and some change in the linear or translational momentum. So I would say that this is equal to some vector that is the, perhaps I could show a rotation here. This would be the h dot g. That's the rate of change in the angular momentum. And ma, the angular accelerator, or sorry, the linear, the rate of change in linear momentum, ma. So here, I could then, again, this is sort of what we've looked at previously, we spent a great deal of time looking at previously. This is our general two-dimensional or plane motion system. So again, I can say the sum of forces is equal to mass times acceleration, simple Newton's second law. Or I could say, if I also look at rotation, I can say that the sum of moments about the center of mass is going to be equal to the rate of change in the angular momentum, hg. Okay? So let's consider this next. However, there are going to be some differences. Namely, one relationship will not be valid. The relationship hg is equal to I omega dot, which we used to determine the rotation or the angular momentum of a plane object. The angular momentum / velocity of a plane object is not valid in 3 dimensions. Is not valid for general 3-dimensional motion. Is not valid for general (3D) bodies in 3D motion. When you start having multiple axes that something can rotate around, things become much more complicated. So, again, so the current chapter, or where we are now, the current chapter is concerned with, well, we can just say the current chapter is concerned with evaluation of the angular momentum and its rate of change for 3-dimensional motion and its application to effective forces, the impulse momentum, and the work energy system. In short, we'll be looking at how we can find equivalent systems that let us describe the motion of 3-dimensional bodies. Okay, so let's look at angular momentum of a rigid body in 3 dimensions. Angular momentum of a rigid body in 3 dimensions. Okay, so let us consider this. Now, let me draw out a generic system here, or a general system. And I'll draw this time something 3D instead of a planar object. So X, Y, and Z with the origin here. All right. Then I could also say there's, if I look then and draw out my general object, so I'll have a general potato object here with the mass center here. Then let's say I have an X prime, a Y prime, and a z prime axis, this one being the local coordinate system. Local coordinate system. All right, so let's consider this here. Actually, what do I want to use? The x prime, let me think about that. Yeah, that's fine. Okay. So, next we wish to look at the motions of the object. Okay. Here. Then, consider this here. I'm going to have Ri prime, which is going to be the vector from the, that's going to be the vector from the origin to the center of mass. So this would be our Ri prime here. Actually, that would be for a given, that's a little bit off, sorry about that. Ri prime is going to be for a given piece of the object here. So if I consider a small piece of the object here, at say pi here, consider a small particle pi in this general three-dimensional body. Ri prime would be the vector from the center of mass to that given point. So that's Ri prime. Then I would have another vector. That would be Vi prime. That is the velocity of our point here, Vi prime, or Pi, in our local coordinate system. And then I'm also going to have an angular velocity, omega. Again, that particle would also have an angular velocity, omega, about the center of mass. So again, let me define these. Ri prime. Vector from center of mass to a point on the body, or in the body. Vi prime is going to be the velocity, relative velocity of Pi, of the point with respect to the center of mass, and omega would be the angular velocity of the body. So I just needed to define these terms before I start working with some of the math. The overall angular velocity of the body about some axis. Okay. And I do know that, one thing I do know is that Vi prime is going to be equal to omega crossed into Ri prime. Just a definition of angular momentum, velocity, etc. Now, moving on here. If I wanted to look at the angular momentum overall of the whole body, so this is the velocity of one piece. If I want to find the angular momentum of a whole body, it would be like this, or as such. Of a whole body about its mass center. And that would be hg, the angular momentum. Well, it's going to be equal to the summation from I equals 1 to n of Ri prime crossed into Vi crossed into Vi delta Mi, just the small amount of mass that point represents, Mi, and this will be equal to the summation of I equals 1 to n of Ri prime, the Ri prime vector crossed into omega, crossed, if I just break up this Vi prime, crossed into omega crossed Ri prime. So Ri prime appearing twice here. And then this times our little delta m. Now again, we're talking in very generic calculus terms. We can't actually sum up an infinite number of points, obviously, but let's consider. Okay, so moving on, I want to look at how we can solve for this in terms of components. So let's consider components. Okay. Here, if I look at components, this here, if I want to break this up into components, let's say I want to look at the x component of angular momentum. The x component of angular momentum, well, if you work all the way through the calculus, and you can see this in the book if you wish, you could find that the hx, if you worked through it and if you applied that formula for the summation along an axis, etc., you would get something like this. You would find that hx would be equal to ix omega x minus I bar y, or I bar xy, times omega y minus ixz times omega z. And we can I could work through all the calculus on here and show all this, but it gets quite tedious and takes quite a bit of time. I'm trying to get through some of the theory fairly quickly so we can start looking at some examples and actually start making sense of some of this. So if you remember from your statics, there are different ways to calculate moment of inertia. We can calculate Ix, we can calculate Iy, Iz, but we can actually also calculate Ixy, Ixz, etc. So please consult your calculus on the method to do that, but we won't need to worry about that too much right now. So Hy then is equal to negative I yx times omega x here, negative that on this one, plus Iy, and I'm putting bars over all of these to indicate about the center of mass, times omega y minus Iyz omega z, and Hz is equal to negative Izx bar times omega x minus Izy omega y plus Iz times omega z. So what's the takeaway from this? Well, if you notice, each of these will depend on a few things. So essentially what we're looking at is here, well, the moment in the x direction. Well, we'll have to consider both the x, y, and z, any x, y, z rotations, and also considering when looking at the angular momentum in the x direction. These things can get quite complicated, as you see here, but there is a kind of logic to it, as this can kind of make sense, or as you can kind of see here, I should say. Okay, and all of this together is referred to as an inertia tensor. If I take the I terms out of here, we get a quantity that is called the inertia tensor. And this represents in a matrix form the overall moment of inertia of the body in 3 dimensions. And this is Ix minus Ixy minus Ixz minus Iyx plus Iy minus Iyz minus Izx minus Izx minus Izy plus Iz. Just a positive number, not plus. These are individual terms in a matrix. Whew. Then, if I want to take this with respect to the principal axis of inertia, well, again, in relation to its own mass center, this would be, if I take this with about to its principal axis, again, about its own mass center, this would collapse to simply Ix prime, 0, 0, 0, Iy prime, 0, and then 0, 0, I prime z. So, in other words, hx prime is equal to Ix prime, omega x prime, omega x prime, hy, the angular momentum about y prime, again the local coordinate system, hy prime is going to be equal to Iy prime times omega, not across, but times omega y prime, and hz prime is going to be equal to Iz prime times omega z prime. Okay. Or, in other words, what I should say is the conclusion from all of this is that the angular momentum of a rigid body and its angular velocity, hg of a rigid body, or I should say and omega, and angular velocity, omega of a rigid body have the same direction if and only if omega is directed along the principal axis of inertia, or along a principal axis of inertia. Only if omega is directed along a principal axis of inertia. And perhaps a better definition of a principal axis of inertia, well, when you study mechanics of materials, you will hear the term principal stress, and it's the same kind of idea, effectively. What this means is a principal axis of inertia, one way to think about it is that if you have a general amorphous 3D body, a very lumpy shape or something like that, depending on which directions you consider it rotating, or what directions you consider, certain planes are going to have a higher moment of inertia in the x the y and the z axes. So the principal x moment of inertia would be, depending on what cut plane you take, that is, or what axis you look at, that would be the maximum, that would be the location or the angle that you'd get the maximum moment of inertia in the x direction. The principal y would be at whatever angle you cut this at, or whatever angle you look at the axis at, that is the angle that gives you the maximum moment of inertia in the y direction, etc. Okay? So hopefully that gives you an idea. Okay? And so, in the same way that a planar object could collapse to two dimensions, or could collapse to two quantities, let's say a 3D object can also be so reduced. So, for example, if you have your XYZ axis here, XYZ, and here our XYZ axis with our origin here and our center of gravity here. We've seen this a million times by now. And then we have HG. What is HG? HG, what is HG? Angular momentum, yes, angular momentum of the center of mass, just seeing if you're awake. HG. And then L, what is L? Linear momentum, yes, capital L is linear momentum, MV. MV, here. And so, then this can be reduced to two things. It can be reduced to L, and this one's fairly simple. This is just your linear momentum. And this is then equal to MV. MV, and HG then is the angular momentum about G. And this one is the one that's ugly. About G. In other words, this is the whole tensor that we discussed previously. The ix, negative iy, negative ixy, etc., etc. So it's hg equals the combination of hx plus hy plus hz, which equals all of these. Again, so this would be plus ix, omega x, minus I, and I'm leaving the bars off here. I know I should probably put some bars off, but I probably should put some overhead bars on these, but I'm skipping them to save a little time. Omega y minus I xy, or sorry, xz, omega z. Hy is negative I yx, omega x, Iyx, omega x, plus Iy, omega y, plus Iyz, omega z. And hz is equal to negative Izx, omega x, minus Izy, omega y, plus Iz, omega z. Iz, omega z. And the angular, if I wanted to find the angular momentum about any other point, so this is the angular momentum about the center of gravity, but what about if I wanted to find the angular momentum about some other point? The angular momentum about any other point, O, or about the origin as I had it drawn previously. Any generic point or general point O would simply be HO is equal to R cross MV plus HG. So it is the angular momentum about the object's own center of mass or center of gravity, and then you add to this the vector from basically the this is the L here, MV, and then you cross that into the position between point O and the center of mass of the object. All right, so moving along. Okay. Okay, another way to look at this is here. And that's one basic idea. And then let me think about this. Do I want to include this? Maybe compute directly from moments and products of inertia. We could do it that way, so you can compute it that way. You can compute moment of inertia about a general point O. I should say angular momentum about general point O, as discussed previously. Or, okay, the HO in the method discussed previously by using by transforming the one from the centroid. In the method previously discussed, or you could actually compute them directly from products of inertia in the O frame, or directly compute them in the OXYZ frame. Now you could, I don't know if you'd want to, but there may be some cases where that would be beneficial. Okay? So that is basic idea of linear and angular momentum in 3 dimensions. But let's look at principle of impulse and momentum. So again, if I say this, I can say here, the principle of impulse and momentum can be applied directly to a 3D system, to a 3D motion of a rigid body. And the way we think of this is that the system momenta at point 1, and the momenta here being plural because we're talking about linear and angular at point 1, plus the systems, all of the external impulses on the systems, all external impulses on the system, and all of these will be equal to the system momenta 2, the momenta at some final point. System momenta 2. Okay? And we can use free body diagrams, so that's the basic idea. Just like we drew the, or if I could draw it out if I wished. Maybe I will. So we had our generic potato body, 3 different diagrams. Well, perhaps initially I had HG1 and MV1 here. Then to it I apply a series of FDTs, integral of FDT, some other integral of FDT, force integrated with time. Oh, and the same G all the way through here. Let me draw that out. And then when this is said and done, you'll have some final momenta, both a final angular and a final linear momentum. So I'll draw them purposely different. So I'd have some sort of HG2 and some sort of MV2, or linear momentum L. Linear momentum L. Okay. And some notes on this. Continued. Well, a few things. Well, we're going to be doing some very similar things to what we did previously, where the free body diagram equations, so we can draw free body diagrams, and the free body diagram equation, or equations, equation is used to develop components, component XYZ component and moment equations. And for bodies rotating about a fixed point, you can eliminate the impulse, of the reactions at O by writing equations for the moments about O. By writing equations for the moments and impulses about O. So if we don't want the reactions, if we're not worried about those, then we can just sum moments about the O, basically. About O. Okay. Okay. So let us consider something like this here. Let's look at I want to work through a little bit of a concept question here. Looking at angular momentum. Look through a concept of angular momentum. Okay. So I'm going to draw something out, and I'm going to draw this out using my always perfect artistic skills. So let's say I have something like this. So I have my X, Y, and Z axis here. X, Y, and Z axis. Now I'm going to have a first thing. So this machine is going to be a little bit complex. well, it's still a simple machine, but it's going to be a little complex to draw. So at a support point at the origin, I'm going to have a collar here. And in this collar, I'm going to have a rod that is going to freely rotate. So the whole thing is going to rotate. I have this rod that is rotating with omega, with angular velocity omega. Here, actually I call it omega 1. So imagine just like a flagpole sticking up from the center and there being an omega 1 attached to it. But then attached to that collar, just attached to this rotating object, is an arm. And this arm is present along the x-axis. And so this whole thing will be turning and turning and turning, so maybe a second later it's at the z-axis or something. And then it comes up and it twists at turns at point B, and at point C there is a wheel, a pulley or a flywheel of some sort. Or sorry, at point C there is a wheel of some sort. And this is in the same plane as our disk here. Or sorry, this disk is in the same plane as our arm here. It's in the same YZ plane currently. And this would be omega 2. Here, omega 2. So, let's consider this. So this is spinning and this is rotating. And I am tasking us with finding the following. Okay, so again, this is going to be point, let's say this is point A here, B here, and C. And so disk D here, or the disk is rotating with respect to arm ABC, and I want to determine the direction or directions of the angular momentum of the disk about point A when shown. Angular momentum of the disk in the instant shown. So basically, I just want to know if they're positive or negative. Well, let's consider x. Okay. So let's think about this here. Well, it's going to be in the negative x direction, but why is that? Let's see. So this thing is going to be rotating like this, like this, like this. If we apply, now the first two are easy. If I think of the y and the z, if I apply a right-hand rule, and if I put my thumb, if I use the right-hand rule and trace my fingers in a curl along the disk, along the disk here, we can see clearly that the iz is going to be positive. See, the vector, if you apply the right-hand rule, and I'm just holding up my hand here, that's not going to record well, but if I'm holding up my hand here and I rotate my fingers along the way this wheel is rotating at this instant, then the vector is going to point directly along the positive z-axis. So the z is going to be positive. So we have positive z. We have positive z. And then here, y. If I look at y, well, again, this whole thing is rotating like this, right? The whole thing is rotating like this. So it must have an angular momentum that is, what? That is positive in the y as well, right? Does that make sense? In the y as well. So positive here. So the question is, I have this as negative in my notes, and so why would that be negative? Any thoughts? Why would that be negative? So in the x direction, it's going to be negative. What kind of rotation do we have about the x direction here? So let me think about that. That might just be some artifact of the mathematics, how they interact with each other. But let me think about that. Why is this negative? So thinking about that. I would have to think about that some more. Why is it negative in the x direction? So it is negative in the x direction. That's what I have in my notes, but I'm trying to recall why. Let me think about that. The z is definitely positive. The y is definitely positive, but why is the x negative? Why is the x negative? So because I'm looking for something that would be rotating, something that would be churning, actually more like this. I guess I'm looking for something that would be churning more like this, and I'm pointing my thumb along the negative x-axis. And what would be churning like that? Well, let's see. Maybe if you put those two together, maybe if you combine those two together and looked at how they I think that's how we could explain it. If we looked at how those two vectors interacted and the location of the vectors, you could, if you played with the vectors a bit, you could see that the ix would be, or that the omega x would be negative, although I'd have to ponder that a bit more. Okay. All right, so let's think about that for a while. Let's take a quick break, come back, and we'll get at it again. All right, thank you.